I'll go ahead and start. Welcome, everybody. I'd like to welcome Nate Kaib from the University of Oklahoma, who's applying to join us as a senior scientist. And Nate, it's a real short intro, so I'll turn it over to you to tell us something about yourself and then give your talk.
Sure. Yeah, so I got my PhD from University of Washington in 2010. Did a postdoc at Queen's University in Kingston, Ontario for 2 years with Martin Duncan. And then I went over to Northwestern University for 2 years on a fellowship there. And then I spent 1 year at what used to be the Carnegie Department of Terrestrial Magnetism, but is now the Earth and Planets Lab. I think it's basically the same people and same setup, but I was there for a year. And then finally I came to the University of Oklahoma, where I've been since 2015. And I'm now an associate professor there, but strongly considering leaving for personal reasons. And that's part of the motivation behind this talk today. But so I decided today to give a talk on my most recent paper, which was published in Science Advances earlier this year. And it was kind of just came out of the blue. And it was a really fun project to work on because it was very unexpected. And I think it makes a fun story about comets. The title's Comet Fading Begins Beyond Saturn. And so we'll jump right in. So just as an outline, so some of this outline might be unnecessary background for this particular crowd, but I'm in a physics and astronomy department, so I err on the side of.
We've got Martians here too.
What's that?
We've got Martians here too.
Okay.
Yeah, give me the full background.
Sounds great. Yeah, I mean, I'll give the full background. So we'll start with a solar system and orbit primer. In case you haven't seen the solar system before, this is a cartoon diagram of what it looks like. I just came in on a conversation of debate about what objects are planets and what are not. But generally, this is what we look. When you just say the solar system, this is what most people think of. The sun's a massive object at the center, and then there's and it's surrounded by objects of varying mass. Typically, we think of the largest 8 planets, or largest 8 objects as planets, 4 inner rocky ones, and then 4 more massive, more distant ones. And then, of course, we have lots of smaller bodies in the solar system as well. And you also can see on this particular diagram that comets do in fact get a shout out. There's one comet in this diagram, but really I want to think about the solar system on a scale today that is about 100 times larger than this. 1,000 times larger. So if we zoom out by a factor of 1,000, so now our spacing is logarithmic. We can see that, at the edge of Neptune, or just beyond Neptune, we have the Kuiper belt, but much, much further out, we come to another reservoir of small bodies. So we have the Oort cloud, and that orbits the sun somewhere between 1,000 and 100,000 AU. There's a huge amount of uncertainty there, but that's the general, it's in the thousands of AU, potentially out to 100,000 AU, or over halfway to the nearest star, which is pretty crazy to think about our solar system extending, that far out. And so when I'm talking about the Oort cloud and comets today, I'm going to mostly be talking about their orbits. And so there's a few different properties, a few different orbital elements that I'm going to discuss a lot today. One of those is the eccentricity of an orbit. That just measures how circular an orbit is, and that's a number that runs from 0 to 1. So 0 corresponds to a perfectly circular orbit. As you approach 1, the orbit gets more and more elongated. And of course, the sun gets more and more offset from the center of the orbit too. And if you have an eccentric orbit, as I just said, the sun is not at the center of the ellipse, it's offset. And so as an object orbits the sun, its distance changes. But if you average over all angles, the average distance is the semi-major axis. And so that's half of the major axis of the ellipse. And so that's a quantity we'll talk about today. And then we'll also talk about the distance of closest approach, which is the perihelion. And then for completeness, I threw in here the aphelion, just the furthest distance that the object gets from the sun. And another orbital element we'll be talking about today is the inclination of orbit. So generally, when I showed you that first zoomed in diagram of the solar system, we tend to think about the solar system as a plane or a disk, because to first order, all the major bodies of the solar system, their orbital planes lie close to one another. But that's not true of the small bodies. Their orbital planes are not necessarily confined to the same average plane of the planets. And this is particularly true of the Oort cloud, which has a spherical distribution. So I will also spend some time talking about orbital inclinations today. So this, if you have any object's orbit defines a plane, a 2D plane in three-dimensional space. If you measure the angle of that plane with respect to some fundamental plane, typically the planet's plane, that is what defines the orbital inclination. Okay, so when we look at comet orbits, we can plot their inclinations measured in degrees versus their orbital periods measured in years. And so right away, this is actually a plot from a simulation, but the data doesn't look too different from this. But what you can see is that it's not just a random sampling of points. There's a clear trend here. And the main trend is when you get to very small orbital periods, what you find is that comets orbits don't have random inclinations. They have inclinations that are highly clustered toward the plane of the planet. So typical short period comet inclinations are between 0 and 30, 40 degrees. Meanwhile, once we get to longer orbital periods beyond a couple hundred years, the inclinations become nearly isotropic. And so what people have surmised based on this is that there are actually two different reservoirs that supply the solar system's comets. So for short period comets, it's thought that they come primarily from the scattered disk, which is a subpopulation of the Kuiper belt. This was first proposed by Duncan and Levison in 1997. And so the Kuiper belt has low inclinations, which explains why the comets that come from the Kuiper belt would have those low inclinations preserved. Then we have for the long period comets, the comets with periods longer than 200 years, most of those, if not all of them, are thought to come from the Oort cloud. And this was first proposed about 72 years ago, in Oort's seminal 1950 paper. And so those are this is the most basic evidence that we have two different sources, two different large reservoirs of small bodies supplying comets in our solar system. And this talk is going to focus almost completely on the Oort cloud and the comets which come from the Oort cloud, which are known as long period comets. And so before I get to more into the actual research of that I'm presenting today, I now want to move on and talk about some kind of fundamental processes that govern the dynamics of both the Oort cloud and long period comets. So we'll go back to this diagram here. And as I mentioned before, the Oort cloud resides primarily in thousands of AU, if not tens of thousands of AU from the sun. Now, most cometary objects, their physical radii are of order a kilometer, a couple kilometers, maybe a little less than a kilometer. So observing kilometer-sized bodies in situ, thousands or tens of thousands of AU away from the sun, is extremely difficult. And the only reason we think the Oort cloud exists is because something has to supply those long period comets. So our long period comets are the main evidence that the Oort cloud exists. Most of our constraints on the Oort cloud are indirectly inferred from long period comets themselves. And now I want to go over the way that the Oort cloud objects can actually become long period comets, because most Oort cloud objects sit out at thousands of AU and they never come close to the sun and never come close to the Earth, and we never detect them. But the Oort cloud, I think, is one cool thing about the Oort cloud is that it's pretty much the only part of our solar system that whose dynamics are actually sensitive to the larger galaxy in which the sun resides. And a couple different processes drive dynamical change in the Oort cloud. So let's pretend we have a hypothetical Oort cloud object here. Now, this is not drawn to scale, but we have the Earth going around the sun, and then we have an Oort cloud object on some eccentric orbit, but it doesn't come close to the Earth. And it has an aphelion, let's say, tens of thousands of AU. So as this object orbits the sun, it doesn't only feel the gravity of the Earth and the sun and the rest of the planets. When it's out at aphelion, it feels gravity from other nearby objects. In particular, it feels gravity from passing stars that happen to fly past the sun. So over time, all the stars in the Milky Way have relative velocities. And so the sun will regularly undergo encounters with other stars, close encounters. And these encounters put torques on the Oort cloud orbits, and these torques cause the perihelion of these Oort cloud orbits to change. And so some stellar passages can exert a torque that pulls the perihelion even further away from the sun, but other stellar passages can exert torques that drive the perihelion closer to the sun. And occasionally you can have the perfect configuration where you have an Oort cloud object and a stellar passage configured right to where the stellar passage drives the perihelion very close to the sun, like, to within a distance of an AU or so. And in this case, you have this Oort cloud object. When this happens, you have an Oort cloud object that very well could have spent almost its entire life, thousands of AU from the sun in a very cold region of the universe. It comes by, gets heated up, and all of its ices start to volatilize, and we see a comet in the night sky. And so this is our general picture for one of the processes that drives long period comets in from the Oort cloud. So most Oort cloud objects are not long period comets, but the Oort cloud, due to the variable nature of Oort cloud orbits, it's steadily producing a new populations of long period comets. We have, so in addition to field star passages, another perturbation on the Oort cloud again comes from our larger galaxy, and it comes from the actual tide of the Milky Way's disk. So here's a 2-mass image of the midplane of the Milky Way. If we zoom in here, we can just imagine a hypothetical scenario where we have the sun and an Oort cloud object. So the sun doesn't sit exactly at the midplane of the Milky Way, and an Oort cloud object will also not sit at the midplane of the Milky Way, but it might sit at a different height above the Milky Way's midplane. And so just like everything else with mass in the universe, the Milky Way's disk has its own gravitational potential, and there's a restoring force that wants to pull both of these objects toward the midplane of the Milky Way. And if they sit at different heights above the Milky Way's midplane, they'll feel different accelerations. So this is an acceleration that is in addition to the sun's gravitational acceleration. And so this basically imprints a non-Keplerian potential on the solar system. As a result, due to this galactic tide, the Oort cloud objects, as they orbit the sun, they don't actually form closed ellipses. So they orbit in not Keplerian ellipses, but they have a non-Keplerian orbit. And over time, this non-Keplerian acceleration from the galactic tide causes Oort cloud orbits perihelion, as well as their inclination to oscillate. And since the perihelion is oscillating with time, this can also drive objects to very low perihelion, and they can enter the inner solar system as a new long period comet. And while stellar perturbations on the Oort cloud were known since Oort's original 1950 paper, actually all the way back to Opeek in 1920 something, the effect of the galactic tide wasn't realized until the mid-1980s. And it turns out that the perturbations from the galactic tide are roughly twice as powerful as stellar perturbations on average. So stellar perturbations are a random process. So occasionally you can get a very strong stellar perturbation that would overwhelm the galactic tide. But if you average out and consider typical stellar perturbations over the course of a comet orbit, the galactic tide provides stronger perturbations. Okay, so as I mentioned before, to first order all of our evidence of the Oort cloud's existence comes from long period comets. And we've been discovering long period comets for a long time, well over 100 years. I mean, you can go back to ancient astronomical records and see evidence of long period comets as well. But here is a plot showing all the long period comets that were discovered between 1900 and 2017. This is put together by Marc Fouchard and others in a 2017 paper. And what I'm showing here is the date, on the x-axis, it's the year of discovery. On the y-axis, it's the comet's perihelion. And what you'll notice is that the vast majority of long period comets are discovered with perihelion less than 4 AU or so. Now, this does not mean at all that comets with more distant perihelia of 5, 6, 7, 8, or even 20 AU don't exist. It's what this is showing us is our observational selection effects, because all objects get brighter as they approach the sun. And this is particularly true of comets, because not only do they reflect more light, but comets are so visible because of the devolatilization process, which creates the coma. As a comet heats up more and more as it gets closer to the sun, the cometary activity increases more and more and more. And so the discovery probability of comets really ramps up because of that as they approach the sun. So most comets that we find have perihelia of a few AU. Now, if we take all the comets that have been discovered since 1900 with perihelia of 4 AU or less, and we plot their semi-major axes, what we see is that the semi-major axis distribution is actually not uniform. It's clearly not uniform. And in particular, this was noticed by Oort in 1950. There's this big spike of semi-major axes around 20, 30,000 AU. And this is known as the Oort spike today. And you also notice that, of course, there's plenty of other comets with smaller semi-major axes down to hundreds of AU. And based on this Oort spike, we classify comets as either being dynamically new comets, which means that they're making their first passage ever through the inner solar system, and not new comets. We'll get to not new comets in a little bit. So why do we do this? The reason that we are very, very sure that these comets on the right with semi-major axes over 10,000 AU, the reason we're very sure that these are dynamically new comets making their first passage through the inner solar system is due to the following. So they're newly arrived from the Oort cloud. The reason we think that is, imagine the scenario where you have an Oort cloud object with a semi-major axis of, let's say, 20,000 AU or 10,000 AU, and its perihelion has just been driven in by a stellar perturbation or the galactic tide, and it's making its first passage through the inner solar system, and we'll discover it as a long period comet. Now, in order for us to discover it, in order for us to have a good chance of discovering it, it has to enter the inner solar system. On its way into the inner solar system, as well as on its way out, it will inevitably receive perturbations from Jupiter and Saturn, but primarily Jupiter. And these perturbations are very strong compared to the orbital binding energy of this comet. So with a semi-major axis of 10,000 AU, these are not particularly strongly bound to the sun. And basically you can just blow on them and it's enough to, I mean, that's an exaggeration, but it's, you don't have to perturb them very strongly for them to have a positive orbital energy and never come back. And so as a comet passes through the inner solar system the first time, it's going to receive a perturbation from Jupiter, an energy kick. And that energy kick is going to result in one of two things happening. Either it'll be a positive energy kick and the orbit will be transformed to a hyperbola and it will never come back, or it will be a negative energy kick and the orbit will be drawn down to a much smaller semi-major axis. Because again, these energy kicks, these typical energy kicks are actually are larger than the orbital energy of the original orbital energy of the comet. And so based on this, we think that everything with semi-major axes bigger than nearly everything with semi-major axes bigger than 10,000 AU have to be on their first passes through the solar system. And what that means is that everything else with semi-major axes below 10,000 AU, and those are returning comets. So returning comets are new comets that avoided ejection on the first pass through the inner solar system, and they're returning on more tightly bound orbits. And those orbits are more tightly bound because they've received negative energy kicks from Jupiter. Okay, so Oort noticed that that comets with semi-major axes over 10,000 AU are very overrepresented, and this was done using only 19 comets at the time. So 19 of the comets with the most well-defined orbits at that time. And so based on this, Oort surmised that the comet cloud, or we now know it as the Oort cloud, must extend beyond at least 10,000 AU. And you'll notice if I go back here that there's this sharp drop in comets below 10,000 AU. There's a drop off the left side of the Oort spike. So does this mean that there's an inner boundary below 10,000 AU? Probably not. And the reason there's probably not an inner boundary at 10,000 AU is for the following. So for us to discover a new long period comet in the inner solar system, its perihelion has to evolve in a particularly special way. Basically, what has to happen is, let's say we have an Oort cloud object that has yet to enter the inner solar system, and it comes through on a perihelion passage somewhere in the outer solar system. And over the course of a single revolution around the sun, what happens is its perihelion has to evolve from somewhere outside Saturn's orbit, so all the way to the inner solar system before it physically makes another perihelion passage. Now, if that happens, if that sequence of events happens, then we will see a new long period comet, and it'll be recorded in our long period comet catalog. Now let's imagine a different scenario where the Oort cloud orbit's perihelion evolves more slowly. So it starts off the same. So this comet makes some perihelion passage in the outer solar system, but now in a single orbital revolution, the perihelion moves in toward the sun more slowly, so that the next time that this comet makes a perihelion passage, instead of coming through the inner solar system, it passes somewhere between Jupiter and Saturn. If this is the case, this comet's never going to make it to the inner solar system because, again, the perturbations it receives from Jupiter are larger. The typical perturbations are larger than the comet's orbital energy. So it will get ejected on a hyperbolic orbit, never to return, and we'll never see this comet pass through the inner solar system. And so basically what that means is that in order for comets to make it over the Jupiter-Saturn barrier and make it into the inner solar system, they have to undergo a very fast rate of perihelion shift. That rate of perihelion shift depends really strongly on semi-major axis. Because remember, the perihelion shift is being driven by perturbations from passing stars as well as the galactic tide. The farther you are away from the sun, the more sensitive you are to those perturbations. And so small semi-major axis comets don't have rapid rates of perihelion change. And what this means is, if you actually work out the math, what this means is that if your semi-major axis is below about 10,000 AU or so, you'll be prevented from ever penetrating the inner solar system. And so this explains why new long period comets tend to have semi-major axes over 10,000 AU. So this partially explains this ramp up in the number of comets we see as we get beyond 10,000 AU, but it still doesn't fully account for the prominence of the Oort spike. So as I've already gone over already, so this spike in the number of comets with semi-major axes above 10,000 AU, that's known as the Oort spike. And then everything else below there is known as returning comets. So it's pretty straightforward to simulate this process of Oort cloud objects being perturbed by passing stars and a galactic tide and being driven to very low perihelion. So you can do this in a numerical simulation. And then when these bodies come through perihelion, you can record their orbits as if they were being discovered. So I and many others have done this before. And this is an example of one of those simulations, which doesn't conflict with what's been done in the literature. So this is a personal simulation that I ran. And what you can see is that this is the simulated distribution of comet semi-major axes. And you can see that there is an Oort spike. So there's a spike out at 20, 30,000 AU, but you can see that new long period comets are very rare compared to returning comets in the simulation. So returning comets should be much more numerous than what we see in the inner solar system. And so what this tells us is that even though the Jupiter-Saturn barrier can actually produce an Oort spike, it can't explain why it's so prominent compared to returning comets. And this has been realized for a long time. Basically, it's been realized since the Oort cloud was first proposed to exist. So in 1951, Oort and Schmidt realized that the dynamical effects of Jupiter and Saturn's perturbations can't produce a prominent enough Oort spike. And what they argued is that to get such a prominent Oort spike, it has to be an observing effect. So new comets must be much more likely to be discovered than returning comets. And their explanation for this is that returning comets simply physically age or fade. So this process is known as fading. And when a comet fades, something causes it to be so dim that it's not discovered on successive perihelion passages. So what this process is still an open question. It could be devolatilization, it could be fragmentation of the nucleus, or something else. But there's physically plausible mechanisms for this fading, and it makes sense. Comets are made of very volatile materials. As they go past the sun more and more, they're presumably going to have less and less activity each time. And so our idea for how long period comets behave is the following. So let's go back to our long period comet, or our Oort cloud objects that's destined to become a new long period comet. So it makes a perihelion passage in the outer solar system, and then its perihelion evolves very quickly as it needs to enter the inner solar system. And now the next time it comes through as a very bright new long period comet. We see it, discover it, record it, but then let's say it survives Jupiter's perturbations and returns on a more tightly bound orbit. When it returns, it's no longer nearly as bright or nearly as active. And because of this, we're much less likely to discover it. And maybe it's just fragmented and it's not there at all anymore. But for some reason, it's not as discoverable on its second time through, so we miss it. And so comet fading, again, amongst long period comets has been known for many decades. And there have been numerous works that have simulated long period comets and compared them with observations to try to infer what how long period comets fade. And the latest work is by Bokrlicki et al. In 2019. What they found is that long period comet observations are at least in the inner solar system, are very well replicated if the survival of comets is proportional to the number of passages they make through the inner solar system to some negative exponent. And their best fit was an exponent of -0.4. And n-pass in this scenario is the number of perihelion passages that a comet makes inside of 3 AU. So 3 AU was deemed to fit the observations well. And this physically makes sense since we know that water begins to sublimate in comets once they get to 2 to 3 AU from the sun. And if you look at other works that have modeled this process, they all tend to settle on a critical region or the critical distance at which comet fading begins. They all tend to settle around the 2 to 3 AU region. Again, it numerically gives you nice answers, and it also physically makes sense if you link it with water sublimation. And so that's kind of the state of our understanding of the long period comets that pass through the inner solar system. And so the comet sample that we have today is not really representative of what's going on in the Oort cloud, because it's greatly distorted by two different processes. So it's distorted by this uncertain fading process, and also before comets ever make it to us, they're filtered out by this dynamical barrier posed by Jupiter and Saturn, primarily Jupiter. So as a result, the current long period comet sample tells us that the Oort cloud exists, but it provides much more limited information on, hard constraints on what the Oort cloud structure it actually is. Is it, what this includes angular structure, as well as if the Oort cloud is 50,000 AU away or 5,000 AU away. And so for a long time, basically since I started grad school, a sample of, and even before then, a sample of long period comets with perihelia near or even beyond Saturn would be much less, it's been realized that they would be much less affected by these processes. And so most hopes in terms of putting new constraints on the Oort cloud have been pinned on developing such a sample of long period comets. And these hopes have been pretty much pinned on the VRC Rubin Observatory, which will begin science observations soon. But this sentiment has been going around, has been in the field for at least 20 or so years. So this is kind of fun. This is a review paper by Luke Dones and others in 2004 that came out, that was published the year after I started grad school. It talks about how using LSST, which is what the VRC Rubin Observatory was known at the time as, LSST would be great at finding these long period comets beyond 10 AU, and we really need it to understand the Oort cloud. Fast forward 12 years later, the year after I started my position at University of Oklahoma, you can look at the Silsby and Tremaine paper on long period comets and find a very, very similar sentence talking about, or basically hoping for LSST to give us a very distant sample of long period comets that can help us better constrain the Oort cloud. And so now I want to talk about these distant long period comets. So when I say distant, I don't mean, thousands of AU from the sun. I mean in terms of their perihelion. So these are comets that would have perihelion well beyond Jupiter. And so that's the topic of my recent work. And so let's go back to this Fouchard et al. Plot from 2017. As I mentioned before, most comets in the historical catalog of long period comets have perihelia around 4 AU. But starting around the year 2000, we've actually started to get better at finding comets in the outer solar system. And in 2017, we knew of something like, at least in this paper, there was something like, I should count up those red dots, something like 10 comets at the time in 2017. And so just for reference, here's Saturn's semi-major axis. So we've actually found a few comets with perihelia even beyond Saturn's semi-major axis. And this is without LSST or VRC-Rubin or the VRC-Rubin Observatory. And so now fast forward to today, this is the list of long period comets when I looked through it just a couple of weeks ago. We're not great at finding long period comets with perihelion out near Saturn, but we're approaching being okay at it. So we're not terrible, at least at this point. So in the last 22 years, we've found 25 long period comets with perihelion out near Saturn. So today, the JPL small body database contains 25 comets with perihelion between 8 and 12 AU. So the most distant one we found is just under 12, it's 11.5 AU. And if you look, if you go out to 8 AU, we've found 25 of these now with a perihelion of 8 AU or further, which is, getting significantly away from the effects of Jupiter. And so now we can compare those. We can compare those more distant long period comets with the ones closer to Earth. So you've seen this plot before. So this is what I showed you. These are the observed long period comets with perihelion in the inner solar system inside 4 AU. And here's, you can see the Oort spike on the right. And now we can make the same exact plot for the more distant comets with perihelion out beyond 8 AU. And this is what it looks like. This is a very surprising plot because remember, I said that the Oort spike was driven by two effects, Jupiter's perturbations primarily and comet fate. What we see when we look at these distant long period comets is we see the same Oort spike. In fact, it's even more prominent than the ones in the inner solar system. So this is really surprising. And this is just a matter of plotting up their semi-major axes, and it's very unexpected. And so what's going on here? So the first potential possibility is you might chalk it up to some inherent quirk in the actual structure of the Oort cloud. Because remember, I said that long period comets, that the ones that enter the inner solar system, don't give us great constraints on the structure of the Oort cloud. So maybe it's just that the Oort cloud is structured in a very specific way that is really good at producing long period comets on large semi-major axes. So I wanted to see if this is a possibility. So basically I generated a very ad hoc hollowed out Oort cloud where all Oort cloud bodies orbit beyond 20,000 AU. So I've hollowed out the inner Oort cloud, and the Oort cloud only is populated between 20,000 and 50,000 AU. So this should be the best type of Oort cloud to produce long period comets on distant orbits. So when you simulate the production of these distant long period comets in this type of simulation, and you don't consider comet fading, here's the plot on the left shows you what you find. So here's the gray line is the observed distribution of comet semi-major axis. The red line, the red dotted line, is what pops out of the simulation. So this is clearly a terrible match. It predicts that 96% of observed long period comets should have semi-major axes inside 10,000 AU. In reality, only 24% of them do. And remember, this is a very contrived Oort cloud. Its inner part is completely hollowed out and devoid of comets. The problem would be even worse if we used a more plausible Oort cloud that had its inner regions populated, because those comets from those areas would be even more likely to evolve onto low semi-major axis orbits. So what I argue for in that on this result is that we can't replicate these distant long period comets without invoking comet fading, even in the outer solar system. So this is so you've seen the red line, so that's just the raw output from the simulations, but then you can go back to the simulations and in post-processing apply comet fading laws to the simulations long period comets as they pass through the solar system. And so I tried a bunch of different fading laws, and I found an example of one successful fading law is shown here. So this is what pops out of the simulations if you apply comet fading. So this dash dotted blue line is the prediction of the observed semi-major axes of distant long period comets if they have rapid fading. So what do I mean by rapid fading? So the fading law I applied here forces comets to fade below detectability after just 5 passages inside 20 AU. This was, this fits the observations very well, but it's very surprising because, again, conventional comet fading is linked to water sublimation, and if you go back and look at other papers about comet fading, they typically don't think about comet fading until perihelia of 2 or 3 AU are reached. And so this is clearly a different mechanism going on here. And so now our idea for what is going on in the outer solar system is the following. So let's say we have a long period comet. It's been, or an Oort cloud object, a long period comet. It's been recently driven into the outer solar system. It makes its very first perihelion passage through the outer solar system, nice and bright. We detect it. But then if it happens to return on a subsequent passage, it's much dimmer for some reason, and we're much less likely to find it. And that can explain the distribution of semi-major axes really well. So, again, very rapid comet fading does a great job of reproducing the observed distribution of distant long period comet semi-major axes. And what this means is that, and this offers a prediction too. So rapid comet fading sets basically a very short lifetime for long period comets as they pass through the outer solar system. If those comets fade rapidly in the outer solar system, what this means is that the ones we see should have their perihelia moving toward the sun very rapidly. And because if that was not the case, we wouldn't see them. So slowpokes, ones that have their perihelion moving toward the sun much more slowly, they just simply fade away before we ever get the chance to detect them. And in a similar way, we could also potentially have backwards comet movers, so comets with perihelion close to the sun and are moving out. But again, it takes a long time to do that, so those comets would fade away before they ever get to the Saturn region as well. And so let's imagine what's going on here. So let's imagine the slow scenario. So a comet has a perihelion out near Neptune, and it moves in pretty slowly, makes a passage at say 20 AU or so. And then that starts fading. By the time it gets to Saturn, where we can now discover comets, it's already faded away, and that doesn't get added to our comet catalog. And then we can also think about another scenario where a comet comes in, goes way into the inner solar system, or makes a passage, and then comes back out near Saturn. Now that takes a long time to do that perihelion sweep in and out, and as a result, this comet probably won't be on one of its first passages in the outer solar system, and it will be faded, and we'll miss this one too. And so really, the comets that get compiled into our catalog have to execute this very specific behavior where they're outside the planetary region, they come in fast, and then we see them on one of their first passages near Saturn. And those are the ones that we actually discover. So this is kind of cool, because if this is the case, this signature might actually show up in their orbital distribution. And so to understand how this signature should show up, I have to go over one other orbital element. So this is the argument of perihelion, or periapsis. So as I mentioned before, an orbit defines a 2D plane, but if the orbit's eccentric, there's some angle in the orbital plane that points to the direction of perihelion, and that's what's known as the argument of perihelion. It's the little omega in this diagram. or the blue or purple angle. So why does that matter? Well, it turns out that the way that the galactic tide affects long period comet evolution depends on the orbit's argument of perihelion. So as an illustrative case, let's consider a comet orbit whose orbital plane is completely perpendicular to the galactic plane. And so that's drawn right here. And that red arrow points to the orbit's perihelion. The argument of perihelion is given by that purple little omega angle. And now, again, is a 0th order approximation. Let's assume that this comet is always at aphelion. And we can think about its velocity vector at aphelion. And we can split it up into a velocity vector in the plane of the galaxy and a velocity vector perpendicular to the plane. And then we can think about how the galactic tide acts. So it acts as an acceleration pulling you back to the midplane of the galaxy. So this acceleration would act in the opposite direction as the z velocity. As a result, for this particular orbital configuration, the angular momentum and the perihelion would decrease over time. So this comet's perihelion would be pushed toward the sun. Now let's rotate this orbit by 90 degrees and consider a larger argument of perihelion. So something between 90 and 180. Now let's think about this object at aphelion again. Its velocity, the direction of its velocity vector has changed. And in particular, the sign of its z component velocity has changed. It now matches the same direction as the acceleration of the galactic tide. So since those two directions are the same, in this particular case, the galactic tide will increase the angular momentum and the perihelion will increase or move away from the sun. Now we can rotate another 90 degrees and we have an argument of perihelion between 180 and 270. Now we can think about the velocity vector at aphelion again, and it's moving. The z component is going away from the galactic plane. That's the opposite direction as the acceleration of the galactic tide. So angular momentum will decrease and the perihelion will get pushed toward the sun. And then we can, to complete this, we'll go to an argument of perihelion between 270 and 360. In this case, if we look at the velocity at aphelion, the z component is going toward the midplane. That's it's being accelerated further by the galactic tide. And in this case, the perihelion will increase or go further away from the sun. So based on this, there are 4 different quadrants of behavior based on the argument of perihelion. So if the argument of perihelion is between 0 or 90 or 180 or 270, the perihelion is getting closer to the sun. If it's between 90 and 180 or 270 and 360, the perihelion is getting further from the sun. So if you actually work out the math on this, what you find is that the perihelion change, whether you're going toward the sun or away from the sun, is proportional to minus the sign of twice the argument of perihelion measured with respect to the galactic plane. And so the direction and the speed of the perihelion shift is simply determined by the argument of perihelion. So what we can do is for our 25 distant long period comets that we know of, we can go and we can measure this and actually calculate this value for each of those long period comets. And we've done that, and what we find is that the distribution of sine to omega g is extremely anisotropic. So again, this is a distribution of the observed values, and the closer you get to 1 on this plot for a given semi-major axis, the faster the galactic tide is pushing you toward the sun. The closer you get to -1, the faster it's pulling you away from the sun. And you can see that there's nothing on the left side of the plot. It's all on the right side, and most comets have values that are very, very far on the right side. And we can look and see how this compares to the simulations of long period comet production that I've done. And so here's the prediction of the simulations if you don't consider comet fading. So it's not nearly as concentrated towards a value of +1 as the observations are. And so you'll notice that there's still some asymmetry there. The reason is that comets are just less likely to come from the sun versus from more distant regions. But in general, like there should be a much broader range of values if there wasn't comet fading compared to what we see amongst the observed comets. And so then we can take our simulation and apply a comet fading law. If I take the same fading law and apply it to the simulation that you've already seen, and I apply it to this simulation, here's the distribution you get. It's still not a great match. So this assumes that comets fade after 5 passages inside 20 AU. And what we find is that it's still not that particular, it helps. So you get a much stronger skew towards +1, but you still have a lot of comets that should have values of sine 2 omega g less than 0. And so this wasn't particularly satisfactory, but you can see that the change is going in the right direction. But one thing I mentioned already in this talk is that we don't really know what the structure of the Oort cloud is. So I just made an ad hoc assumption for what the Oort cloud looked like. I populated it between 20,000 AU and 50,000 AU. But now we can play a game and we can explore alternative structures of the Oort cloud. So we can take our Oort cloud and strip off everything beyond 40,000 AU. So this, if we do this, we only consider comets that started on semi-major axes below 40,000 AU. If we do this, the match starts to look better. And we can go even more extreme. We can ignore everything beyond 25,000 AU. So in this setup, we're only really considering comets between 20 and 25,000 AU. So in this case, the match is starting to look pretty good. It's actually not rejectable with KS test at this point. So that's pretty cool. So why does this happen? So the reason this you don't get good matches when you add in more distant comets is because once you get out to 30,000 AU or so, cometary orbital elements fluctuate wildly in a single revolution around the sun. So when in a single revolution around the sun, the argon of perihelion can flip back and forth between +1 and -1. And this will always prevent a tight clustering toward that +1 that we see in the observed distribution. And so what this observed distribution is telling us, this fact that we see a really tight clustering is telling us something deep about the structure of the Oort cloud that we didn't know before. It's telling us that Oort cloud bodies with semi-major axes of roughly 20,000 AU or even less dominate production of the Oort cloud, which is something we didn't know based on the comets in the inner part of the solar system. And so it also tells us something cool about the perturbations of the Oort cloud. So as I mentioned before, the 2 main perturbations of the Oort cloud are the galactic tide and stellar passages. And I said on average, the galactic tide should dominate, but we don't know that for any short epoch. But now we do know that, because if stellar passages dominated, so stellar passages are randomly oriented, we should have no reason, we'd have no reason to expect to see a clustering towards sine 2 omega = 1 if it was stellar passages that were producing long period comets. So this tells us that the galactic tide has dominated the dynamics of comets during their last revolution around the sun. And because the galactic tide is just can be approximated with an analytical formula, this allows us to estimate their comets' previous perihelion passages. So not their current perihelion distance, but where they passed through the solar system the last time before they were discovered. And so you can do this. You can simply back integrate these comets by a single orbital period in the presence of the galactic tide. And this is the distribution of previous perihelia passages that you get. So this is where comets passed through the solar system the last time on the last orbit before they were discovered. And what we find is that, as expected, most of these long period comets are coming from very distant perihelia. So 19 of the 25 known comets, their previous perihelion passage in their last orbit occurred beyond 12 AU. So this suggests strongly that comets start disappearing from our observations at a minimum of 12 AU. Otherwise, you'd find a lot of, so just to refresh your memory, all these comets that we know of, they have current perihelia between 8 and 12 AU. If they didn't start disappearing at a much larger distance, we should find a lot of comets still with perihelia between 8 and 12 AU, but we don't. We find that the large majority of them had previous perihelia well beyond 12 AU. And I should mention that all of the ones that have perihelia inside 12 AU, they'll have very small semi-major axes, which are not really affected by the galactic tide anymore. So these are probably comets that have come through at least once and have had their semi-major axes drawn down to smaller values. So we can also do this. We can also play the same game with the comets that we simulate in our simulation of comet production. So we can take those comets as they were discovered at perihelion, apply the fading law, and back integrate their orbits by a single orbit. And that blue distribution, the blue dash distribution, is what our simulations predict, and it's a very good match with the with what we see in with the same treatment of the observed distribution. And so I've just presented one simple fading law where comets fade after 5 passages inside 20 AU, but these are effectively free parameters. So you could choose other, you could test whether comets fade after 10 passages, and you could test whether they fade inside of 14 AU versus 20 AU. And we have a few different constraints to compare our simulated comets with the observed comets. So we have their semi-major axis distribution, we have their arguments of perihelion, and we also have their previous perihelion passages. And so we can use basically these free parameters, the number of passages before a comet fades and the perihelion inside which fading starts. We can treat those as free parameters, and we can test different fading laws comparing our simulations with observations. And we can outline the swath of parameter space that gives non-rejectable matches to the observed comet orbits. And so I've done that for semi-major axes, for arguments of perihelion, and for previous perihelion distances. And those swaths of non-rejectable parameter space are outlined in various colors on the left plot here. And you can see that all the outlined swaths overlap with each other. And if you combine all this, what you find is that the evidence indicates that comet fading does begin at 12 AU, potentially as far as 20 or 25 AU. And comets fade very quickly. They fade somewhere between 2 and 10 passages inside after penetrating 12 AU or even further. And so with that, I'll just summarize my points for today. So long period comets with perihelia out near Saturn, we've now developed a sample of those, and those are highly interesting because they're less affected by Jovian perturbations as well as water sublimation. But when we look at the orbits of these, they show the same prominent Oort spike that the historical catalog of long period comets do. And so what this tells us, or what this strongly suggests, is that the observed comets are best replicated if they fade from observability after a handful of passages inside 15 to 20 AU of the sun. So this is complicating because it's some unknown fading mechanism. It's going to complicate the interpretation of future VRC-Rubin comet detections, which will be coming online the next couple of years. On the other hand, it can provide insight into the nature of distant cometary activity as well as the properties of comets themselves. And so with that, I'll stop my talk and I'll answer any questions you might have. Thanks for your time.
Thanks very much, Nate. Any questions for Nate?
I raised my hand.
Oh, good. Go ahead, Bea.
Very interesting talk.
Oh, thanks.
So you say, unknown fading law. So speculations?
I mean, I assume some sort of hypervolatiles, like CO or CO2 that gets burned off the surface, but I don't know. I mean, I'm not really a physical planetary scientist. I mean, I think about a little imaginary particles in a computer simulation usually. But I mean, we know that CO has been detected in comets as well as other hypervolatiles. So it's probably something like that would be my guess. But then, I mean, there's other people that think about amorphous ice too. But again, it's probably some devolatilization or phase transition that occurs at low temperature, but I don't know. Or maybe it's fragmentation. I have no idea.
Nolan.
Yeah, great talk, Nate. So you touch on the physical disruption, and if the physical disruption is present, there would be a brightening.
Yeah.
So observationally, I would expect to be detected at least some. I don't know how many objects should fade per year. Have you done that?
I mean, if you naively took my n = 5, I guess about 20%. But I mean, I would take my fading laws with a grain of salt too. But I mean, I would just assume that there is a fading law. I don't think the ones I've found are unique in any way. But anyways, that's a good point about so I do know that distant long period comets have been observed to have outbursting behavior. There's just a couple papers about this year in AppJ or AppJ letters. I can't remember the authors off the top of my head. You might be one of them. I don't know. But so I don't know what the rate of that is or if it is known, but that, I mean, that is potentially a testable prediction. Yeah.
Yeah, especially with the Vera Rubin Observatory, LSST.
Yeah, that'll be great because those will give us long baseline or long timelines to observe these things.
Yeah, can I ask another question?
Sure.
So you talked about this argument of perihelion effect, the galactic tide. I was just curious. I think that it is small number statistics, but still, did you notice whether there is any sky direction dependency in that?
I didn't, but I haven't actually searched because I was pretty, I kind of had blinders on because I've always thought about the galactic tide. And that's what I specifically looked for that. And I saw the signal that made sense, but you're right. I mean, you could do a 3D plot of the directions of perihelion and see if they're coming from the same. I mean, you also have to think about the fact that our survey coverage isn't complete too, so that we're going to be biased in some directions. That's what I didn't talk about in here. Is obviously there's going to be selection effects just due to survey coverage too, and I just ignored that issue because the consistency with the galactic tide model is so strong that to me that the fact that it lines up like that suggests strongly that it's not like a survey pointing bias or something like that. But yeah, I mean, it would be certainly worth just looking at a 3D plot, and I have not done that.
Okay, thanks.
Before we go to Liz, I'd like to jump in and just say, yeah, you'll have to sit down and do some simple cartoons with me to explain why argument of perihelion, independent of inclination and longitude of ascending node, would have any correlation with tide. So because I have a hard time wrapping my head around that.
Well, so inclination matters too. So you hold all those other things constant. It's the argument of perihelion so argument of perihelion controls the direction, whether you're going in toward the sun or out. But inclination and longitude of ascending node, actually not longitude of ascending node, because to first order the local disk is axisymmetric. But inclination does matter. You won't get any perihelion. So inclination controls the speed as well as the semi-major axis does too. But argument perihelion basically just controls the direction.
And what's the obliquity of our solar system with respect to the galactic plane?
Just over 60 degrees.
Oh, wow.
Yeah.
Okay. Liz.
Hey, so I hadn't really thought about this before relative to comets is their spin. And so I was wondering, has anyone looked at these really elliptical orbits and what kind of effect that would have on the spin of the comet?
Oh, on the spin? Did you say? Sorry.
Yes.
Oh,
do they not have much of a spin?
That is something. So I don't know how well that's been measured. So I know you can get spin up through jetting and things like that. And so I would say there are definitely people that believe that fragmentation drives a lot of comet fading, and you can have breakup through basically jetting, causing the comet to spin up. And so that definitely alters their spin. But then I don't know. I guess you could have, I'm just trying to think, if you had a very eccentric orbit and the object comes through perihelion near the sun, you could have tidal effects from the sun potentially change the spin orbit or spin the comet spin too. But I don't know how well that's been looked at, to be honest. I also don't know how well constrained comet spin is. Sorry.
Can I comment a little bit on that? Nate, you are right. It is primarily the outgassing torques which change the spin of comets. Of course, if it comes very close to the sun, then the outgassing rate also increases.
That's true. Yeah.
So, but if a comet is very close to a planet, typically a few radii, then tidal effects can have an impact. So, yeah, those are the primary mechanisms by which cometary spin can get changed. I'm talking about the spin of the comet itself, nucleus itself, not the orbital spin.
Oh, yeah, yeah. Yeah, thank you for that. Yeah.
You know, with regards to the quick decay, fading, I can't help but think back to Duncan, Quinn, and Tremaine, 1987, that for me painted a picture of the Oort cloud as the great garbage dump of the early solar system, because nothing formed out there. It was all just dumped out there from kind of all parts of, you know, from perhaps the asteroid belt where that Earth mass went away, and other, you know, Kuiper things beyond that. And of course, it's got more sophisticated since '87 with all the NICE people and stuff doing things. But if there's a significant population of rocky bodies in the Oort cloud that were ejected from the inner solar system, then I would expect over the age of the solar system that, yeah, they may be covered with a nice rime of your hypervolatile stuff, and that they'd be great candidates for, if they come in on you know, new comet orbits, that rime is going to disappear fairly quickly. And because they're not an icy body, there may be no more stuff to emit.
Yeah, that's true. I mean, that could be telling us something fundamental about the composition of comets. Yeah, I mean, I don't know. And maybe the ones that we see in the inner solar system are only the ones that have survived this outer solar system fading too, and are, you know,
Well,
there's a selection like that.
The short period comets, if they come from a different region, you know, the Kuiper belt, and they formed actually the outer solar system, and so they really are icy bodies, where the Oort cloud population of objects may be significantly different than the source population of the short period comets.
Yeah, yeah. Yeah, that I mean, so there are things that I want to look into, and one is like, yeah, the relative source populations of the Kuiper belt versus the Oort cloud. And so if somebody give me money to do that, that'd be great.
Yeah. Good, Jeff.
Yeah, so here, I don't know why this didn't go away. Anyway, my question to Mark is, where does this purported rind come from? Is this just cold bodies sucking up gas that's out there?
Yeah, it's just the crap that's out there, you know. I mean, it's the early part of the solar system. I mean, who knows what was hanging around?
It's an interesting idea. I mean, and I could imagine that there might be more than, you know, like two basic populations: the rocky bodies that get you know, this rind that goes away quickly, and then some other, you know, more intrinsic things that did get, but we're not seeing those, right? This is what Nate is saying.
Yeah, that silicic rock from the asteroid belt that got kicked out in the Kuiper belt, and after 4 billion years, it comes home again. You know, what would you expect it to look like?
Yeah, I don't know.
So this is the thought. But yeah, that paper is a good paper.
Yeah, so my thesis advisor at University of Washington was Tom Quinn, and then I did my postdoc with Martin Duncan. So I got 2 out of 3 of those covered.
That's great. That's great. Cool. Any other questions for Nate? Nate, well, thank you very much. It was a great talk. Really enjoyed it. A lot of discussion, and you know, I'll be in touch with you.
Great. Thank you very much for having me. And
Thank you.
Thank you.
Thank you.